Now we're going to look at a necessary condition for convergence. In order for a series to converge, that is, for the sum as n goes from 1 to infinity of a sub n to equal s, a finite number, we must have that the limit as n approaches infinity of a sub n is equal to 0. Now this is what's known as a necessary condition, but it's not sufficient. That is to say, however, knowing that the limit as n approaches infinity of a sub n is equal to 0 does not guarantee convergence. That is to say that it doesn't guarantee that the sum as n goes from 1 to infinity of a sub n converges. And what this does is it gives us a criterion for ruling out convergence. If we know that a series doesn't have a limit that's 0, then we know that it's not going to converge, because if it did converge, it'd have a limit of 0. And I mention this because much of the work in the rest of the chapter is going to be determining whether or not a series converges. But before I get into that, let's go ahead and write this down as a theorem. If the sum as n goes from 1 to infinity of a sub n is convergent, then the limit as n approaches infinity of a sub n is equal to 0. That's the formal mathematical statement. And we're going to prove it. Let's start by letting s sub n equal a partial sum a sub 1 plus a sub 2 plus a sub 3 plus a sub all the way up to a sub n. Then a sub n would become s sub n minus s sub n minus 1. What? Look. S sub n is all the sum of all the terms that we just wrote down. S sub n minus 1 is the sum of all the terms just before a sub n. So if I subtract the purple s sub n minus the green s sub n minus 1, what's left is a sub n. I know, it's amazing how that works. Saying that the sum as n goes from 1 to infinity of a sub n is convergent implies that the sequence of partial sums s sub n is convergent, which means it has a limit, and we're going to say let the limit as n approaches infinity of s sub n equal s. Then the limit as n approaches infinity of a sub n is equal to the limit as n approaches infinity of s sub n minus s sub n minus 1, because we've already established that a sub n is equal to s sub n minus s sub n minus 1. By using a limit law, we can say then that this becomes the limit as n approaches infinity of s sub n minus, the limit as n approaches infinity of s sub n minus 1. But folks, they both have the limit of s. And so the right-hand side equals s minus s. And you might say, wait a minute, this one's s sub n minus 1. Yeah, n minus 1 goes to infinity if n goes to infinity, right? So we can conclude that the limit as n approaches infinity of a sub n is equal to 0, which is what we were trying to prove in the first place. Now, I told you that much of the work in this chapter is going to be testing series for convergence, and here we have our first test, but it's actually called the test for divergence. I'd recommend that you have a sheet of note paper that you're going to keep returning to as we write down tests that you'll just add to that sheet. For the test for divergence, we can say that if the limit as n approaches infinity of a sub n does not exist, or if that limit does not equal 0, then the series, the sum as n goes from 1 to infinity of a sub n, is divergent.